So let's get started with today's lecture. And we're going to be talking about a computational model called Deterministic Finite Automata. Okay, so as we said last time, in this chapter and next chapter, this week, next week, we're going to be really now defining what computation means, what algorithm means mathematically, formally. We have already seen one piece of the puzzle here. So we know how to represent data, right? So we can encode, represent pretty much any kind of data, whether it's numbers, text, pairs of numbers, video, audio, whatever it might be, with a finite length string, perhaps a binary string. So one piece of the puzzle here is that the data we're talking about, input data, output data, we're talking about input string and output string, okay? So now we want to uncover more pieces here and really understand what is this middle part, the computer part, how can we define that component, how can we go from the input string to the output string. Okay, so before I start, I want to actually tell you some terminology that I'll be using in this lecture and in future lectures. I want to make sure that when I use these terms or phrases, you exactly know what I mean by them. Okay, so the first terminology or the first phrase is a computational model. So when I use the word computational model, what do I mean? These are the allowed rules for information processing. Okay, so when you're defining some model of computation, obviously, it's not like anything goes in terms of like what can you do when you're processing information. You want to have some reasonable assumptions on what kind of operations are allowed. For example, maybe when you're doing computation, you cannot travel back in time, for example, right? I mean, it's not clear if the laws of physics allow you to travel back in time. So, for example, that would not be an allowed operation when you're doing computation, as one example, right? So you want to specify exactly what kind of operations you allow, and that is the computational model that specifies what kind of information processing rules are allowed. Now, once you have a computational model, when we talk about a computer or a machine from that computational model, what we mean is basically an instantiation of the computational model, or in other words, it's a specific sequence of these information processing rules that the computational model allows, right? So once you come up with a specific sequence of information processing rules, where the rules are specified by the computational model, then you have a machine or a computer, with respect to that computational model. Now, this terminology might be a bit strange because when we use the words computer, machine, in our everyday lives, we're really talking about usually like physical devices, physical realizations of these things. But in a course like 251, we don't really care about the physical realizations and implementations. We care about the mathematical representations. So for us, we're going to be identifying, whether it's physical or not, we're going to be thinking about these things, these machines, these computers, in terms of their mathematical representation. And, it's some set of instructions, basically. The text behind, here you go, information processing rules. Sorry, I have a big head. So the mathematical representation is really what we care about. And we have another word for it, actually, right? And these words. We call them an algorithm, a program, right? So actually, for us in 251, computer and an algorithm, machine, program, these are all synonyms, okay? Because we're not going to make a distinction between the physical device and the mathematical representation. Now, still, this might be a bit surprising or confusing because when we use the word computer, when we're talking about our laptops or phones or whatever, we don't think of it as corresponding to one particular algorithm. We know that our computers can be programmed to run any algorithm, to run any computer program. That is true. That is because our computers, the computers that we use today, are actually a special kind of a computer that we would call a universal machine, a universal computer that runs a special kind of an algorithm that we would call a universal algorithm. And a universal machine or universal algorithm, what it does is actually, given some other algorithm, given some other program, simulates it, runs it. Okay, so that's the kind of machines that we're using. Now, that being said, this is actually not a trivial concept at all. So as you're thinking about formalizing computation, and even though these are the machines that we're used to, I do not want to just assume that the concept of a universal machine exists. I want to motivate that concept to you. So I want you to imagine that we don't have, or we don't know of universal machines. That concept is not familiar to us, let's say. And then let's, over time, motivate that concept and see how it arises. So I would like to make a couple of assumptions here. The first assumption is that, as I said, we're not going to assume that universal machines exist. What that means is that for every task you want to solve, you need a different machine, you need a different algorithm. So if you imagine living in a world where you go to your local computer store, and if you need to do addition, you ask for an addition machine, and then the person will be like, okay, takes the addition machine and then gives it to you and says, okay, this is $50, please. And then you're like, oh, I need also a primality testing machine. Can you give me an is prime machine? And then the guy's, okay, here you go. This is the primality testing machine. That will be $100, please. And so on, right? Maybe you also want a sorting machine. So you just imagine that this is the world, the kind of world we live in. Obviously, that's not the kind of world we live in, but we have to come to that. We have to motivate the notion of a universal machine. The second assumption is what we talked about actually previously in the previous lecture. Our focus is going to be more on decision problems, at least for the first few weeks of the course. And as we said, this is kind of without loss of generality. For each computational problem, general computational problem, usually there's a corresponding decision problem that is roughly equivalent. If you can solve one efficiently, you can solve the other one efficiently. So we might as well just restrict our attention to decision problems, which are simpler objects, right? So we saw that decision problems are languages, and languages are just a set of words. So that's a convenient restriction. Okay, so now we come here. So we want to define a computational model where our input is going to be some string, and the output is now either 0 or 1, reject or accept, because we just want to restrict ourselves to decision problems. Okay, and today and this week, actually, what we're going to be covering is the deterministic finite automata model of computation. Okay, and this is actually a restricted model of computation. This does not have the full generality that, for instance, a Turing machine has. Now, you might be asking, why study a restricted model of computation? And that's a good question. So let me give like a couple of different answers to that. First of all, in computer science, we definitely are interested in modeling restricted computational settings, because the certain situation that you have, the certain setting you have, might be actually a restricted setting. For example, on the internet, you have huge amounts of data, and maybe you only get one pass through the input. There's like a lot of input coming in. It's streaming through. You cannot just remember, there's so much data. You cannot keep everything in memory. So you have limited amount of memory, and then just getting one scan through the input, you have to make a decision. You have to do some computation. These are real world situations. And then you want to model that situation and understand it better. So that's one thing. In real world situations, we can have restrictions. The second thing is, you might, even if you don't really have a restricted, situation, you might want to restrict yourself in the way that you describe your algorithm, because that can be useful in various ways. A restriction that might mean that you guarantee that your algorithm has some, desirable properties. Maybe you apply a restriction so that when you express your algorithm in that restricted setting, you're guaranteed that, for instance, that it will run efficiently, that it will be, let's say, linear time. Okay, maybe you're guaranteed that it will not have an infinite loop, right? So you eliminate bugs by restricting yourself. So that's also what can be one of the motivations of restricting yourself, to make sure that your algorithm has some desirable properties. Now, the DFA model, let me describe you at a high level what these restrictions are in the DFA model. So it's actually a model of computation with a very limited amount of memory, and we'll say more about that later. And it basically reads the input. You know, a DFA will read the input from left to right. It's kind of like a streaming model. You get the input once, one symbol at a time, and at the end, you have to accept or reject. Okay, so that's kind of how DFA operates. And one of the main reason I should say that we study DFAs in 251, you know, they're interesting in their own right. They have very nice, interesting applications, and you would see them in the future, in future courses possibly. But the main reason we study in 251 the DFA model is to use it as a stepping stone towards the more general definition of a Turing machine. Okay, it's really like a nice intermediate computational model that is similar to Turing machines in many respects, but also not as maybe complicated as a Turing machine, not as involved as a Turing machine. So it's a very nice stepping stone. Okay, so this is the model that we're going to be looking at. And now I'm going to describe to you this what's known as the state diagram of a DFA. Okay, so I want to tell you now the pieces that make up a DFA, how you can describe a DFA. And usually when we're describing a DFA, what we do is we draw what's known as a state diagram. So this is what I'm going to do. We're going to see all the different pieces a DFA has, and then we're going to see how it processes information. Okay. So this is called a state diagram for a reason, because DFA is composed of states, and the states are drawn as circles. Okay, so I'm gonna start drawing some circles. Let's fix our alphabet to be just the binary alphabet, 0, 1. And let's say we have one state, another state, one more state, and another one. So we have 4 states, and we're gonna label them, let's say Q0, Q1, Q2, Q3. Okay. So this particular DFA has 4 states. Now I have to specify for you one of the states as the initial or starting state. We have to kind of know where we start. So this will be Q0. So typically Q0 is the starting state, and usually we put an arrow going into it out of nowhere. So that indicates the starting initial state. Good. Now the next thing is I have to tell you how to transition from one state to another state. In particular, when we're reading a symbol from the input and we're at a certain state, how do I go to the next state? Okay, and that's the transition rule specifies that. So to define the transition rule fully, from each state, I have to draw 2 arrows leaving that state, one labeled with the symbol 0 and the other labeled with the symbol 1. Okay, and those will tell me where to go if I read a 0 and if I read a 1. So from Q0, let's go to Q0, and maybe we have a self loop. Self loops are completely allowed, and maybe this is 0. So if you read a 0, you're in Q0, you stay in Q0. And maybe 1 would take you to Q1, the symbol 1. Now, if you're in Q1, maybe whether you read 0 or 1 doesn't matter, and you go to Q2. Now, technically, you would want to draw perhaps 2 arrows from Q1 to Q2, one with label 0, one with label 1. But, you know, that clutters the diagram a little bit. So we use this shorthand. We just draw 1 arrow and then put 0, 1 on it. It's just a shortcut. From Q2, let's say 0 takes you to Q3. And if you read a 1, you stay at Q2. And from Q3, let's say 0 takes you to Q0. And 1 would, let's say, take you back to Q2. Okay, so now these are all the transitions, right? Notice that from each state, I have 2 arrows leaving it, one with label 0 and one with label 1. Good. The final piece is that I have to tell you what the set of accepting states is. So I have to identify some of these states as accepting. And the way I will do that is by drawing another circle. So I'll mark, for instance, Q1 as an accepting state. So I draw another circle. And Q2 I'll mark as an accepting state. So in this DFA, I have 2 accepting states, Q1 and Q2. Good. So now this is the orange box, right? This is my, in some sense, computer. I've defined a particular computer to you. It will take in some input and make a decision about whether it will accept or reject output true or false, output 0 or 1 with respect to that input. So let's give it an input, okay? And see what might happen here. So the input is, let's say, 1, 0, 1, 0. Okay, so what would happen? So what is your guess? What's an educated guess? about whether this DFA, particular DFA, is going to accept or reject the string 1010. What do you think? So I see rejects, right? So what is the educated guess here? Well, we start in Q0, right? And then we read a 1, so that takes us to Q1. Then we read a 0, that takes us to Q2. Then we read a 1, that's a self loop, that takes us to Q2. Then we read a 0, and we come here to Q3, right? So let's see that in action. So we start at Q0. We read the first symbol, that's a 1. We take the appropriate transition, right? And that takes us to Q1. And now you can imagine that the first symbol is consumed and, erase it, it's gone. Now, what's the next symbol? It's a 0. Read that symbol, take the appropriate transition, that takes you to Q2. Now that symbol is consumed. Now you're left with 1, 0. The first symbol there is 1. Take the appropriate transition, come to Q2. That's gone. And then you're left with 0. Read that, take the appropriate transition. And now we have consumed all the symbols. Now we look at, is the state that I ended up in, is it an accepting state or not? If it's not an accepting state, it's a rejecting state, right? So in this case, Q3 is a rejecting state. So the decision would be to, as you guys said, reject. Okay. Good. So I'm seeing some nice questions. Can you have any finite number of states and so on? Yes. So hold on to that. We will definitely talk about this as we proceed in the lecture. Okay, so what about if I were to look at the string 10101? Okay, so what I did, it's the same string 1010, but I appended a 1. Now I don't have to simulate the whole thing again because I know what 1010 ends up at. It ends up at Q3. So then I have to, from Q3, take the 1 transition and come to Q2, right? So this will end up in Q2, and this will now be accepted, this string. Good. Okay, so let's make sure that we understand all the pieces of the DFA. So let me point out once again what's going on here. So the circles are the states, okay? We have an initial state, which is usually labeled Q0, or an arrow coming in from nowhere. That's the initial state. We have 2 accepting states. We have some subset of the states that are accepting. These are usually denoted by double circles. And we have the transition rule that is specified by the labeled arrows. Okay, and in particular, from each state, you need 1 arrow leaving it with label 0 and another arrow leaving it with label 1, assuming the alphabet is, of course, 0 and 1. Okay. Now, you're absolutely right about, asking, does it have a finite number of states? Can a DFA have more than 1 initial state? Can there be arrow leaving? Can there be 2 arrows leaving a state with the same symbol and so on? These are now not specified yet. So we will need to define what a DFA is formally to understand and really know what the answers to those kinds of questions are. And we will definitely do that, of course. But for now, what I want to do is let's just, increase our intuition about DFAs. Let's play with DFAs a little bit more before I give you the formal definition. Okay, and then once we have a better understanding of how they operate, then we'll see the formal definition and all the pieces. Okay, so before I give you some examples now, some more examples, we just need to make one definition, and this will be convenient in terms of our terminology. So given a DFA, let's call it M, and some language L, which is a subset of sigma star, we're going to say that the DFA M solves that language if the following holds. Well, it's exactly what you would expect. If a string W is in the language, then you want your machine, your DFA, to accept that string. And if W is not in the language, then you want M to reject W, right? So if I didn't give you this definition and I said, go home and define for me the notion of a DFA accepting or solving a language, this is exactly the definition you would come up with, I hope, right? So there are different words that we can use here. So solve is one word that we use, but decide is another word that we use. Compute is another word that we use here. These are synonyms in this context. Decides, why do we use the word decides? Because, well, basically, this is the same as defining what it means for a DFA M to solve a decision problem, right? Because languages correspond to decision problems. So, we're deciding, in some sense, the decision problem corresponding to the language, to the decision problem. And that's why we use the word decides. Now, note that there is a unique, so given a DFA M, there's a unique language that the DFA solves, okay? And what is that language? Well, it's the set of all those words that the DFA accepts, right? So that's the unique language that the DFA solves. So we should, a useful notation is the following. Let's, have some way to denote that set. So L of M, given a DFA M, L of M is gonna denote the set of all the strings that M accepts. And as I said, L of M is the unique language that M solves or decides or computes, okay? Good. So now with this notation definition in hand, let's look at some examples. So the first example is the following two-state DFA. So who can tell me what the language of this DFA is? So, okay, so I'm seeing even number of ones. And yes, I agree. So all binary strings with an even number of ones is the language that corresponds or that this DFA solves. Or in set notation, we can write it with set builder notation as follows. All those x in 0, 1 star such that x has an even number of ones. Okay. Now, one thing I should point out here is that when you look at this DFA, of course, you see that, seeing a 0, when you're reading a 0, that doesn't change your state, and reading a 1 changes your state. And in general, in DFAs, the states usually have some kind of a meaning, some kind of a purpose, right? So as you're reading the input, if you are at a certain state, then that means something. So what does that mean about the string that I have read so far? So in this particular case, as I'm reading the string, if I'm at Q0, what does that mean? Well, it means the string I have read so far has an even number of ones, right? And if I'm at Q1, that means the string that I have read so far has an odd number of ones, right? So when you think of it in that way, like states have meanings, that helps you to reason about DFAs. Okay, next example, another two-state DFA. What is L of M? Even length, very good. All binary strings with even length, right? So in some sense, very similar to the other one, but now whether you read a 0 or a 1, that will switch your state. And in set notation, you can write it like this. It's all those binary strings x such that the length of x is even. And recall that we use this absolute value sign to denote the length of a string. Okay, so how about this one? Another two-state DFA. What is the language of this DFA? So ends with 0 is what I'm seeing here. So all those strings x that ends with a 0. You're almost correct. Okay? Exactly. And empty, right? There's an edge case you have to be careful about. The empty string is also actually accepted, which brings us to a nice point. So you might ask, what happens when a DFA is fed the empty string as input? And that's allowed because empty string is a string. So what happens? Well, you start at Q0 as with any other string, but then there's no symbol to consume, so you stay at Q0, which means that a DFA will accept the empty string if and only if the initial state Q0 is an accepting state, right? So if the initial state is an accepting state, then the empty string will be accepted. Very good. How about this one? Now our alphabet contains 3 characters, A, B, and C. Yeah, so very good, very good. So one way to reason about this is to notice that all the arrows are going from left to right. That's one thing. And the other thing is Q3, the state Q3 is like a black hole, right? once you're there, you can't go out, and it's actually a rejecting black hole. This is what we would call a rejecting sinc state in DFA lingo. This is a rejecting sinc state, so once you reach Q3, then game over, you know, doesn't matter what you read afterwards, you're going to be rejecting. Okay, so then we can reason about this by just observing what's going on. So what are the ways that we can end up in the accepting state Q2? Well, one way to end up there would be to take this transition. So from Q0, you can either read an A or a B and end up at Q2. So that means the string A and the string B is going to be accepted. And another way to end up is going to be through, you know, these two transitions. So you might read a C and then follow that with a B, and that will end up in Q2, or you can go C and then another C, and that will be also Q2. And then you can check, that's pretty much it. That's the only way you can end up at Q2, and anything else basically is not going to work. And you have 4 strings, only 4 strings in this language, right? So it's a finite language. Very good. Now here's a poll for you, and let me start this. So I'm going to be asking you what the language of this DFA is. Of course, our poll. Oh, this is kind of weird. So itempool.com/CS251/live. Yep, thanks everyone for adding that to the chat. I don't know why this is covering up on that, but okay. Too many options, maybe. Okay, so if you want to take a look, here is the DFA, a better picture of it. And one hint I'll give you, you might want to look at the 0 transitions and the 1 transition separately and see what kind of thing happens with these kinds of transitions. Okay, so what we have is option F, the set of all words ending in 00 is the most common choice here, and you're absolutely right. So who can write in the chat, what are like the key observations here, 1 or 2 observations that really helps us reason about this particular DFA? Yeah, very good. So the first observation is like about the 1 transition, right? If you look at what 1 does, it's like takes you wherever you are. Whenever you read a 1, it takes you back to the initial state. It's kind of like, you know, you see a 1, you messed up, start over kind of thing, right? So that's the 1 transition. And then I'm also seeing last character must be a 0, then second to last must also be 0. Yep. And then we need at least 00 to go, right? No matter, yeah, exactly. No matter where we are, 00 takes to accepting state. Very good. I like that characterization. Okay, so if we now look at the 0 transitions, no matter where you are, 2 zeros will get you to the accepting state, right? And now with these 2 observations, you kind of see that, okay, so then it must be the case that this is the set of all strings ending in 00. Now, this one is a relatively simple example, so you wouldn't really perhaps need to prove necessarily that this is a correct description of the language. But in general, like let's say, you know, we give you some like DFA, complicated DFA, you describe the language, and it's not clear maybe immediately why that language is the language that this DFA solves. How would you actually prove that this is the correct language that the DFA solves? Well, you need to do 2 things, right? So first, you have to show that if a string is in the language, which in this case means if string W ends with 00, then your DFA accepts it. accepts it. And if W is not in the language, which in this case means W does not end with 0, 0, then you have to argue that M rejects it. So if you do that, those two arguments, then you show that this is indeed the language solved by the DFA. Very good. Now, another kind of question that you can get with DFA. So what we did before is I give you the DFA and I ask you, can you describe the language that this DFA solves? Another kind of question you can get is, here's the language, can you come up with a DFA that solves this particular language, okay? So let's do some examples here. We're not gonna do all of these, but we can do a few of them. Let's start with something like very simple, like the empty set, right? So the language is the empty set. So what kind of a DFA are we gonna draw here? What DFA solves the empty set? Yeah, just like one state, right? Exactly. I mean, you have one state, initial state, and then you have a self loop, 0 and 1, and that's it. This is your DFA, right? Everything is going to be rejected. Actually, you can draw any DFA here which does not have any accepting states, right? Any DFA with no accepting states would do here, right? Because if you don't have accepting states, you cannot accept any string. Good. So now what about sigma star? Now in this case, L is supposed to be the whole set of finite length strings. Same thing, but now accepting, right? Exactly, right? Or in other words, you can like draw any DFA you want and make all the states accepting. That would also do the trick. Very good. By the way, this, I guess shows you that there's not necessarily like one DFA that solves a language, right? So given a language, there can be multiple DFAs that solve the language. And, one interesting question you can ask is like, what is the minimum number of states needed to, solve a particular language, right? That might be an interesting question to study. But anyway, let's not get distracted. Let's do another example. So here the language is 110 and 101. So it consists of just two strings. And we want to draw a DFA for this. So what are some ideas here? What can we do? Yeah, I can brute force it, kind of. I like that description. So how can we make sure that we accept these strings? So like one way you can also reason about a DFA is to say, okay, here are the strings that I need to accept. Let me design it so in a way that, I make sure that the strings that should be accepted are accepted, right? So how can I make sure that these strings are accepted? Well, I need an initial state. Then what I'll do is, to make sure that 110 is accepted, I'll create a path with, 110. Okay, so that's what I'll do. So 1 takes you to another state. So then another state, and then we have a 0. Okay, so that's the path 110. And of course, we want to accept 110, so we're going to make that an accepting state. Good. Now I also want 101 to be accepted. So the way I can do that is now I, again, start with a 1. Now there I branch off. Now this is 0 from the second state. And then from there, I have, when I see a 1, I go to a new state and I accept, let's say. So now I have a path for 110, I have a path for 101, both end up in an accepting state. Now, one question, do I really need two accepting states? I don't, right? That's redundant, so let's do it this way, right? So this would work, this just the same way. Good, now I've made sure that the strings in my language are accepted, very good, and now I have to make sure that the strings that are not in the language are rejected. Well, what do I do? What will I do? What will I need to do? Yes, black hole, sinkhole. Yeah, so basically all the missing transitions should go to a rejecting sync state like this, okay? So what I did is, there were missing transitions in my state diagram. I made them all point to a rejecting sync state. Now that's good, but this is kind of an ugly picture now. I don't like this. So we can actually, simplify, keep the picture simple. So I'm going to go back to the original one I had, and I'm going to add the following comment. I'm going to say all missing transitions go to a rejecting sync state. And this is totally fine to do, right? So we want to keep our diagrams as simple as possible. And if you say that, if you write this sentence, then it is understood that, oh, okay, so there is actually another state here, and all the missing transitions go to that sinc state, rejecting sinc state. So you can draw it this way, you can make this comment, but note that, you know, the number of states in this DFA, right? So what I have drawn here, you have 5 states, but the true number of states in the DFA is 6, even though I didn't draw the 6th state. Okay. How about the complement of this language? So now we have 0, 1 star minus take out 1, 1, 0 and 1, 0, 1. So what would be the strategy here if we want to recognize, we want to solve this language? Exactly, right? So flip, accepting and rejecting states. So I'm going to take what I had before. I'm going to remove the accepting state, that's gone, and then make all the other ones now the accepting states. And now I'm still missing the transition, so that's still okay. So I'm going to say all missing transitions go to now an accepting sinc state, not a rejecting sinc state, but an accepting sinc state. Very good. So let's do one more, and then that will be it. Here's this the language consisting of all those strings that start and end with the same bit. Okay. So obviously we need the initial state, so we put it there. What could be the idea here? What might be a general strategy here? At the high level, what kind of strategy? Excellent. Split based on the first bit. Love it. And that's the right way to do it, right? So you want to case it based on whether the first bit is a 0 or it's a 1. Right, so let's do that. So this, the upper one state here, let's say corresponds to the one where we start with a 0. And the lower one corresponds to the case where the first character is a 1. Okay, so now if I'm in the upper case, when I'm in the case that starts with a 0, then I have to make sure that it ends with a 0, right? So I'm going to have now logic on the upper case to make sure that it ends with a 0. Good. Now, first thing is, if the input is just the string 0, if the input is just the string 0, then it should be accepted, right? It starts and ends with the same bit, which means like this state, upper one, should be accepting. Now, if I keep reading zeros from that state, well, you know, that's still in some sense the same state. You know, I have zeros. But if I now see a 1, I want to go to another state, to a rejecting state from there. Because now I'm not ending with a 0, so that's not good. And if I keep seeing a 1 there, you know, keep there. But now if I now, from that state, from this state, I see a 0, come back. Okay. And now hope you agree with me that this here, this logic here, you know, we start with a 0, and if we end with a 0, then we're going to be accepting. But if we start with a 0 and we end with a 1, then that's going to be rejecting. And then we follow the same pattern with the other case. It's just that we're going to be flipping the zeros and the ones, right? So the same picture, but the role of 0 and 1 is reversed. So that's what you see here. Okay, so now, good question. What about the empty string? Right, so should we accept the empty string or not? That's a good edge case to consider. So it really depends on, so here is my point of view, right? So there's going to be some disagreement here, and it's completely natural to disagree on this, I think, accept or reject, because I would say this description of the language is not really precise enough. It's not precise enough to really tell us, like, is the empty string should be considered a part of this language or not. So you would have to be a bit more, I think, you know, descriptive about the language, and then based on that, say whether it accepts or rejects with the empty string. I would say in my interpretation, this would be rejecting initial state, but I can understand it if your interpretation is that, you know, the empty string is a string that starts and ends with the same bit. Okay, but this is like a minor side point. Okay, so these are the examples. So now, as you can see, we have basically described a computational model for you. What model? is this. This is the Deterministic Finite Automata computational model. And the machines, the computers, the algorithms corresponding to this computational model are called Deterministic Finite Automaton, right? So automata is like the plural of automaton. And just to make it clear to you, exactly clear to you, that indeed a DFA is like an algorithm, it's like a computer program in some funky programming language, right? Let me view a DFA as a programming language for you. Okay, so here's a DFA that we had before. And here is like a programming language syntax way of like representing this same DFA in some sense, okay? So this is a weird like programming language. It has series restrictions, but here's the way basically it works, okay? So suppose your input is given as an array of bits, 0, 1, 1, 1, let's say. You have an index I. The index I basically points to the symbol that you're reading in the array, okay? And then we start at state 0. When we first look, is my index I equal to the length of the input? So have I reached the end of the input? If I have reached end of the input, then I'm going to make a decision to accept or reject, or basically return true or return false. In the case of state 0, which corresponds to Q0 here, of course, this is a rejecting state. So this is why it's a return false. Then I read the letter under that index in the input. So that's the letter. And then I also increment I by 1 just to get ready for the next step. And then I look at the letter. I have a switch statement. That's like, okay, what is the letter? And depending on that, I'm going to do something. So if the letter is a 0, I go to state 0. If the letter is a 1, I go to state 1. And this corresponds to exactly these transitions, right? If you're in Q0, you read a 0, you stay in Q0. If you're in Q0, you read the 1, you go to Q1. And this is exactly what this switch statement is doing here. And you have, state 1, the same thing for state 1, and state 2, and state 3, and so on. And the thing about this programming language, though, is like, what can you do with this programming language? It's very restrictive. The only thing you can play around with is you can add as many states as you want. That's up to you. But when you're describing a state, you have to use this syntax. The only thing you can change is whether you're returning true or false. So the things that I highlighted. So this piece of information you can change. And also you can determine where you go to, state 0 or state 1. Okay, you can play around with these values, but that's it. Nothing else. Everything else has to be like as shown here. So it's a very restrictive programming language, but it's a programming language nevertheless, right? So I just want to point out here is that when you're drawing a state diagram, it's kind of like actually writing a computer program in a very restricted programming language. But of course, you wouldn't want to represent your DFA as shown here with this code. That's ugly. It's not very intuitive. It's much nicer to do it with a state diagram. It's much more visual and easier to see what's going on. Okay, so now let's come to the formal definition of a DFA, right? Because as we said, look, there's still some question marks about like, can I have more than one initial state? Can the set of accepting states be empty? Well, we kind of saw that it could be empty. Can there be two transitions leaving a state with the same symbol and things like that? So we have to specify this. So this is why you need a formal definition. So in the formal definition of a DFA, it is characterized as a 5-tuple. A 5-tuple is basically a fancy way of saying that a DFA has 5 components, okay? And these components we're gonna denote by Q, sigma, delta, Q0, and F. Now it's gonna be kind of notation heavy because there are 5 components to it, but if you look at it component by component, hopefully you'll agree that it's not that difficult, okay? So what are these pieces? Well, first, we have the set of states, right? This is the Q. So Q is a finite non-empty set called the set of states. So now here we see, by the way, that Q cannot be infinite, right? So Q has to be a finite set. Why it's not infinite? Well, if it was infinite, how can I physically realize this machine, right? So I cannot construct an infinite thing in this universe. So that's a very reasonable assumption restriction to make, to restrict it to finite. Sigma is our good friend alphabet finite non-empty set. Now transition function is really where the action is. This is encodes all the labeled transitions in a DFA, and it is actually a function, if you think about it, from Q times sigma to Q. So let me explain how this works, and I'm gonna disappear here for a bit. Okay, so here is like a small piece of a DFA, okay? And here we have two transitions out of Q0, one with labeled 0 and one with labeled 1. Now the delta function, the transition function, of course, encodes this information in the following way. So it says, as input, the delta function wants a state that you're currently in. So, okay, that might be Q0. The symbol you're reading, so that's maybe 1. And then the delta function tells you now which state you should be going to based on that information. So that's the output of the function, which is in this case Q1. Right, so we would write this as delta of Q0 comma 1 is Q1, right? Given that you're in Q0 and you read the symbol 1, then you should be going to Q1. That's what delta tells you. And similarly, of course, delta of Q0 comma 0 is going to be Q0. Okay? Good. So that's the delta function. And then we have Q0 is the initial state, or the start state, and F is the set of accepting states. It's a subset of Q. It can be empty, it can be the whole Q, no restriction here, it's just some subset of Q. Okay, so here's an example in the formal definition. So let's see how the formal definition maps or corresponds to the state diagram that we have drawn before. So in this particular state diagram, the set of states Q is Q0, Q1, Q2, Q3. The alphabet is 0, 1. Now the transition function, how am I going to represent the transition function for you? Well, one convenient way to represent the transition function would be to use a table actually. So let's have a table where the rows are labeled with the set of states. Each state has its own row. And the columns are labeled with the symbols of the alphabet. And then we fill in this table according to the output of the delta function, right? So if the input to the delta function is Q0 and 0, if you're in state Q0 and you read the symbol 0, well, then you're going to stay in Q0. If you read Q0 and if you're at state Q0 and you read the symbol 1, then you go to Q1. If you're at Q1 and you read the symbol 0, that takes you to Q2. And if you read a 1, that also takes you to Q2 and so on. So you fill it out like this. Okay. So, and this is the table representation of the function. What is the initial state? Q0 is the initial state, starting state. And what is the set of accepting states? It's Q1, Q2. Okay, and now you see like these are two equivalent representations of the same object. Like we have a DFA object. If we, draw the state diagram, all the information about the 5 tuple is there. You know exactly what the set of states is, the transition function, and so on. But also you can give it as a 5 tuple representation, and that will be another way to represent the DFA. Okay. Now, let me also define for you what it means for a DFA to accept a string, okay? And for this, here's a useful notation that we're going to be using. We're going to extend the transition function, the definition of the transition function a little bit, so that not only, it's not just taking as the second coordinate a single symbol as input, but it can maybe take any finite length string as input. Okay, so I'm going to denote this new function as delta star. Okay, so the difference between, as I said, delta and delta star is that the second coordinate here, with respect to delta, that was just a single character. Now I'm allowing any finite length string. And the definition is exactly what you would expect. This is going to denote the state we end up in if we start at state Q and read the string W in the DFA. Okay? And if you want to like use mathematical notation to define this, like this definition is perfectly fine. But if you want to use mathematical notation, it would be basically a repeated application of the delta function, right? So you start with Q, read symbol W1, then you apply the transition function again with W2, apply a transition function again with W3, and so on. But this representation is not necessary. I think the English description here is completely fine. But now that we have this definition, we can easily say what it means for DFA to accept a string W. It just means that delta star Q0W should be one of the accepting states, right? So this is exactly what we have here. And otherwise, we're going to say M rejects W. And often, actually, I'm going to even drop the star from the notation here and overload the delta sign. So the delta sign will correspond to the transition function as well as, this function here. And I think that's completely fine. Even though we're overloading, it doesn't create any kind of ambiguity. Okay? They're in some sense consistent with each other. Okay, one more definition, and an important definition. This is the concept of a regular language. So any language that can be solved by a DFA is called a regular language. Okay? Any language that can be solved by a DFA is called a regular language. Good. So now, big question. What is the big question now you can ask, right? So we have defined a computational model. What is the first question that you feel is, sort of important to ask and answer? Exactly, right? Are all languages regular, right? How powerful is this DFA model? Can I compute anything with a DFA? Or are there some restrictions? What are the limitations of DFA, if there are any? So let me draw a picture for this. So we have the set of all languages. And in mathematical notation, the set of all languages, we can denote it by the power set of sigma star, right? Because a language, by definition, is a subset of sigma star. Therefore, the set of all languages is the set of all subsets of sigma star. And that's the power set of sigma star. Now, we know that some of these languages are regular languages. We've seen a few examples in this lecture. And the question is there anything outside here or not? So the question is, are all languages regular? Now, what is your intuition for this? Yeah, right. I mean, it seems, as I said, DFAs are a restricted model of computation. It seems like there should be some problems that a DFA cannot solve, right? And I completely agree with that. But now then the question is, how do we prove that, right? So this is now going to be our task, okay? We want to come up with a language that is not regular, and we want to prove that it is not regular. So I'm seeing already like prime checking. Very good. So now let's think about the task at hand, right? We want to come up with a language such that no matter what DFA you come up with, your DFA cannot solve this language. Seems like a very hard task, right? Like, how do we rule out any possible DFA? Like DFAs can have many states, millions of states, perhaps weird transitions. How can we reason? How can we argue against all possible DFAs? It seems hard, but we will be able to do it. And that's actually pretty cool that we can do it. Now, as you're approaching this, one first question, I guess, that comes up is, how do you choose your candidate non-regular language, right? So you want to identify some language and say, like, this cannot be solved by a DFA. Some of you already have given me, like, let's say, primality testing. Now, there are a couple of strategies you can employ here. One strategy would be to actually pick a complicated language and say, like, this is a complicated language, has a complicated structure, complicated definition. So therefore, a simpleton like a DFA cannot handle this language. Okay, but that wouldn't be a good strategy in my opinion, because if you pick a complicated language, your probably argument is going to be complicated, and maybe it's going to obscure the essence of what's going on, right? So it's actually better to pick the simplest language that you can think of that really targets the weakness of the DFA, okay? So which means that you probably want to think about what are the key limitations of a DFA? And then with my choice of the language, can I target in the most simple way I can, target that limitation or limitations? Well, what are the limitations? I mean, I kind of told you at the beginning of the lecture. So one thing that we said is, you scan the input once from left to right and you have to make a decision. But that wouldn't be a problem if you had like actually external memory to make use of. You could read the input once from left to right and then store that input and then do whatever you want with it. So scanning input once is not maybe perhaps the key limitation. The key limitation, I would say, is that it has a constant number of states, and really the states are the way that a DFA remembers stuff, kind of used as a memory, and there's no other way to remember anything else. So when I say a constant number of states, I mean that it's a fixed number that cannot depend on the input length. That's what constant means, constant with respect to input length, which means that if you have some DFA, let's say it has 251 states, well, it's fixed once and for all. And this DFA with 251 states has to be able to handle all input strings, any length input string, right? So that the input length might be 1,000 bits, 1,000,000 bits, 1,000,000,000,000 bits, no matter what it is, it has to give the correct answer. So that seems very limiting, right? So a constant number of states kind of means it has constant amount of memory. Okay, good. So now then we want to target basically that weakness, that limitation of a DFA, that it has a constant number of states and no other way to really remember stuff. Now, if we want to then target that and pick a non-regular language, candidate non-regular language, maybe we can think about, if you did not have any restrictions, like let's say if I'm giving you a string and you're gonna, scan it once, you're gonna see the input bits one by one, and then you're gonna do something and make a decision about accepting or rejecting. What is something that you could do that a DFA could not do, right? If I'm giving you an input string, zeros and ones, what operation, what kind of thing that you could do, a DFA could not do? Update a variable. Check that the first half of the string is yes. Okay, I'm gonna focus on one thing here. You guys have great ideas. Count, right? A DFA cannot count to arbitrary numbers. You can count, like if I give you a billion length input, you can count like 1, 2, 3, 4 and do that. A DFA, let's say it has like 10 states, maybe it can count up to a 10, but like it can't really count more than that, right? So I think like accounting is like a very simple operation, a very simple thing that we can do that a DFA should not be able to do. So then based on that, here's my candidate, like let's say language. Like consider the language consisting of all binary strings with an equal number of zeros and ones. So I think this would not be a regular language, and we can go ahead and try to prove this, right? Actually, I'll even simplify a little bit this language for convenience. It's easier to write this language. Let's consider the set of all those strings of the form 0 to the n, 1 to the n. So you have some number of zeros followed by the same number of ones, right? So just to be clear, so the empty string is in the language, 0, 1 is in the language, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, and so on. So this is an infinite language, and it has this form. And yeah, so now we want to argue that no DFA can recognize this language. So what would be, again, the intuition here? The intuition that we're developing is that it seems like when you are, solving this language, what you would do is you would see the zeros and you would count the number of zeros you see, and then you would count the number of ones you see, and then you would compare those two numbers. So it seems like a DFA would need to remember the number of zeros it sees as it's scanning the input, but it has a constant number of states and really no other way to remember things. So it should not be able to do that, right? So if you told me, for example, hey, I have a DFA with 1,000 states that, solves this language, I would say, okay, you're claiming a DFA with 1,000 states solves this. let me give you an input with a million zeros and followed by a million ones. I think that input should really mess up your DFA. Your DFA should not be able to handle that. Okay, you say, well, okay, I came up with another DFA. It has a million states now. I said, fine, it has 1 million states. Now I'm going to give it an input with a billion zeros followed by a billion ones. How is it going to handle that, right? That's kind of the intuition. Now, okay, very good. So this is the intuition. Now, can I call this intuition a proof and be done with it? Is this a proof? Is this intuition a proof that 0 to the n, 1 to the n, this language is non-regular? Absolutely not, right? Now, your intuition in this case is true, but you have to be careful, right? Here's another language, related language, where you can apply, it seems, the same kind of intuition. You can say, so this is the language of all those binary strings, such that the number of 0 ones and 1 zeros occur equally often. Okay, and in this case also it seems like, well, to decide to solve this language, it seems like I would need to count the number of 0 ones and the number of 1 zeros, compare those two numbers and see. So it seems like this also requires you to count, but careful, this is actually a regular language, right? So your intuition actually is not correct, would not be correct in this particular case. Why? Well, it turns out in this part, for this particular language, actually there's a hidden structure that doesn't require you to count, right? You can do this without counting. So that is to say, intuition is of course very good, and you're going to build your argument based on your intuitions, but intuition is not a replacement for airtight proof. So that's what we want. Good. So now I'm going to give you the argument. A key component of the proof is going to be the pigeonhole principle. So let me quickly remind you, the pigeonhole principle is if you have k plus 1 pigeons, but only k holes, and you're going to put the pigeons into the holes, then you know that at least 2 of the pigeons have to get cozy and share a hole, right? So that's the pigeonhole principle. I'm sure you've seen it before. Very simple principle, and it's going to come in here. Okay, so let me now give you the proof idea, right? So this is the language we want to show that it's not regular. And what do you think is going to be the overall proof strategy? Is it going to be a proof by induction? Is it going to be a proof by, yeah, okay, you got it, right? Contradiction, right? Because in some sense, when we were building the intuition, that's kind of how we reasoned about it, right? I said, well, if you say that you have a DFA for this language with some number of states, then I'm going to feed it an input that is much longer than the number of states you have. And that should mess things up for you, right? And that's exactly what we will want to do. So let's assume that, for the sake of argument, that there's a DFA with 6 states that decides this language. Now, why am I saying 6? Because I have room to fit 6 states on my slide here. That's the only reason. The argument is going to be the same, no matter what 6 is, arbitrary k, it's going to work. But I'm just saying 6 for now as an example. Okay, so let's draw that DFA, right? I have 6 states. There's some transition. Imagine some arbitrary transitions here. I cannot draw you the transitions because there's no DFA for this language, but we're imagining some DFA exists. And then what? Then, as we said, let's feed this now DFA a long input, right? More than 6 characters, right? So let's give it all zeros. All zeros is fine because as the machine is reading the zeros, it doesn't know oh, will there be an equal number of ones followed later on? So that way we can sort of confuse it. And let's imagine we run it on this input, right? So the empty string starts at Q0, and then you read a 0 that takes you, let's say, to Q2. You read another 0, maybe that takes you to Q3. You need another 0 that maybe takes you to Q1. Another one, maybe now you're in Q5. Another one, now you're in Q4. And then another one, and now we are back to Q3, right? So after reading 2 zeros and 6 zeros, something interesting happened. Now, the first time, 2 strings ended up in the same state in Q3. Okay, now, this should be a problem, right? Because if you think about it, from the DFA's perspective, it's kind of oblivious to the difference between 2 zeros and 6 zeros. Both of them end up here, and that should kind of be a problem. Who can see why is this a problem? would it be a problem to have 2 zeros and 6 zeros end up in the same state? Exactly, right? So you're like, consider like having 2 ones or maybe like 6 ones afterwards, or let's say just 2 ones, right? What should happen? So let me explain this. I think you guys kind of see the argument now, right? But let me explain what's going on. Now we have 2 zeros and 6 zeros ending up in the same state. Okay, state Q3. Now what this means is that once these two strings are joined, in some sense they're joined then forever, right? So if I append any string, so if I were to append, let's say, a 1 to 0, 0 and 6 zeros, so 0, 0, 1 and 6 zeros 1, well, again, they will be in the same state, right? Or if I were to append to these two strings 1, 0, 1, well, they will end up in the same state, right? So 0, 0, 1, 0, 1 and 6 zeros 1, 0, 1 is going to end up in the same state. Let's say Q2, for example. So the observation is basically that, and I will disappear now, for any string z, if you append z to 2 zeros and 6 zeros, they end up in the same state, right? So once they're joined, like they're joined, these two strings. And now this is a problem, right? Because why? As you guys suggested, if you consider the string z to be 1, 1, right? Well, these have to end up in different states because 0, 0, 1, 1 should be accepted and 6 zeros 1, 1 should be rejected. And now this is where we are using the assumption that our DFA recognizes that our DFA solves this language 0 to the n, 1 to the n. And that, of course, has to come into our argument, right? I mean, we have to use the fact that this DFA, we're assuming, is solving the language 0 to the n, 1 to the n. And this is where we use it. We say, well, if it's solving correctly this language, then we know that 0, 0, 1, 1 should be an accepting, should end up in an accepting state, and 6 zeros 1, 1 should end up in a rejecting state. But a state cannot be accepting and rejecting at the same time, right? And that is the contradiction. Okay? So this is basically the proof idea here. Okay? So let me highlight the pigeonhole principle once again here. So what happened is that we thought of these strings, like the empty string 0, 0, 0, and so on, as pigeons. And we know that every string ends up in some state in the DFA. And the state is like the hole that the pigeon goes to. So the empty string goes to Q0, right? Starts at Q0. Maybe like 0, that pigeon goes to Q2. And, you know, you basically, these strings start going to holes, different holes perhaps. But then, you know, if you have, I have 6 states, if I have 7 pigeons, if I have 7 strings, then I know 2 of these strings must end up in the same state. 2 of the pigeons have to go to the same hole. And that was key in our argument, right? And it didn't really matter if it was like 2 zeros and 6 zeros that ended up in the same state. If it was like 3 zeros and 4 zeros, that would still be fine. We could still carry out the contradiction. Okay, so not enough holes for all the pigeons. Yeah, so now I'm gonna actually tell you how to write this up, right? So this, we kind of built our intuition. We're pretty much close. Like, I mean, if you just now write this up a bit more properly, you get a full proof write-up. And let me show you quickly how that goes, right? So this is a proof by contradiction. So we're gonna say, assume for the sake of contradiction that there exists some DFA that solves the language L that we're interested in, here, 0 to the n, 1 to the n, and let k be the number of states of this DFA. Now, what are we going to do? We're going to consider our pigeon set, okay? So consider the following set of k plus 1 strings that we think of our set of pigeons. So what's the k plus 1 strings that we sort of considered implicitly in the argument? Well, we looked at the empty string 0, 0, 0, 0, 0, 0, all the way up to and including 0 to the k. So that's a set of k plus 1 strings. And now by applying the pigeonhole principle, we know that 2 of these strings, let's call them x and y in P, must end up in the same state, right? So this is where we apply the pigeonhole principle to say that two of x and two strings in P, let's call them x and y, end up in the same state. Then what did we observe? We said, well, first of all, okay, let me expand on this a little bit, and I'll disappear actually here because I don't have room for myself. So what this means, when you look at the structure of the strings in the set P, what this implies is that there exists I and j, I different from j, such that 0 to the I and 0 to the j end up in the same state, right? We think of x as 0 to the I and y as 0 to the j. Then now, the other observation is that now once you end up in the same state, now it doesn't matter what appending string I use. So for all strings z, I know 0 to the I z and 0 to the j z must end up in the same state, right? And then we are almost there, right? So now you say, okay, well, now consider though the string z to be 1 to the I. Well, when you take z to be 1 to the I, then 0 to the I z is going to be equal to 0 to the I 1 to the I, and this must end in an accepting state. On the other hand, 0 to the j z, which is going to be 0 to the j 1 to the I, must end up in a rejecting state because I is different from j. And this is the desired contradiction, right? Because on the one hand, we say, look, 0 to the I z and 0 to the j z, no matter what z is, must end up in the same state. On the other hand, when you consider a particular z, which is 1 to the I, we see that they must actually end up in different states. One accepting, one rejecting. And that's the contradiction. And then we can put a box here, and this is the full argument. Okay. So I see one question, why this proof can't be applied to 10110. I love that question, right? So that's exactly the kind of question you should be asking. This is like what it means to dig deeper and understand something better. I'm not going to tell you. This is exactly what you should be figuring out. So go through the proof and see if you can make it work with 10101. It should break, right? And see where it breaks and why it breaks. And then once you see that, you can go and actually start thinking about, oh, can I actually draw a DFA for this? Actually, and you should be able to. Okay, but I mean, that's a great question. This is exactly the kind of question you should be asking. Okay, so now you have a proof like this, and you guys already started asking good questions, but you want to dig deeper, right? So you don't, when you read a proof in the notes, you don't want to just read it once and be like, you verify that the proof is correct and move on, right? You want to dig deeper and understand what's going on better. So you want to ask, like, what are the high-level steps here that we used? Why did this argument work? Can I extract the key ideas that made it work so that then I can use it in the future? Okay, so this is the kind of thing you should be doing yourself when you read a proof, and I'm going to do it for you now. So after reading this proof, I would be like, okay, so there are maybe 3 high-level steps here. You set up a proof by contradiction, we pick our pigeons, and then we reach a contradiction from there. So what do these mean? So setting up a proof by contradiction, assume that the language is regular, okay? And so DFA with k states, let's say, recognizes it, or solves it. Then you pick your pigeon. So you identify k plus 1 strings. So you had k states. We identify k plus 1 strings as our pigeons. Okay. And by pigeonhole principle, we know that two pigeons, x and y, must end up in the same state. Okay. Now that means that for any string z, xz and yz must end up in the same state, right? So once two pigeons fall into the same hole, they fall in love, and then they're joined together forever. You can't separate them anymore. They are not distinguishable. They're not separable, right, from the DFA's perspective, right? And then you reach a contradiction from there. You identify a particular z that does separate these two pigeons, okay, such that, xz, one of xz and yz is an L, but not the other, okay? So now you sort of now understand the proof a little bit better here, but you have to dig deeper still. Because you have to see that, look, the way step 2 and step 3 works, they have to work together, right? So in particular, you cannot just pick any set of pigeons. So one question you should be asking yourself is, can I just pick any set of k+1 strings and make the argument work? Not necessarily. You need to pick your pigeons carefully such that you can carry out the contradiction step here, that you can do step 3. In particular, consider, for instance, this one, right? Would P like 1, 1, 1, 1, 1, 1. So we chose, in the previous example, we chose the string 0, 0, 0, 0, 0, 0, and so on. And that worked. Would the strings, you can ask, why did we choose those strings? Would it work if it was like all ones? Well, hopefully you see that it wouldn't work, right? Because every string in P starts with a 1, which means that no matter what appending string Z I use, it's going to be rejected by, should be rejected by the DFA. So I cannot carry out the last step to say that, oh, one of them is going to be accepting and the other rejecting. I cannot get an accepting string from this pigeon set. So this wouldn't work, right? So now you start to understand, oh, I have to pick my pigeons carefully. And also, when you're applying the pigeonhole principle, you don't have control over which 2 pigeons end up in the same hole. So it has to work no matter what 2 pigeons end up in the same hole. Okay, so now you make these kinds of observations. Now you're understanding things better. So I hope you see that there's a difference between reading a proof and verifying that it's correct. Like you can go through the logical steps and say, oh yeah, that works, and then move on. But you can ask deeper questions like this to really understand what's going on and get a better intuition, better understanding. And that's exactly what we would like you to do. Okay. Great. So here are a couple of exercises for you to end the lecture. And, I encourage you to do these so that you get a better intuition. So one language you can look at and try to now, after lecture, prove it is not regular is this language, C, A to the n, B to the 2n. It's kind of similar to 0 to the n, 1 to the n, with a slight twist to it. So see if you can make this work. Okay. So this is kind of the language. And here's another one. This is slightly trickier. This is a unary language. So it's the set of all those unary strings whose length is a power of 2. I somehow have a missing here bracket. So this is not regular. And this answers an interesting question, actually. You can say, well, you could have asked, like, is every unary language regular or not? And this says, no, actually, there are also unary languages that are not regular. So this will require perhaps a bit more thought. Okay? So I'll leave you with those exercises, and then we'll continue basically our discussion on next lecture tomorrow, Wednesday evening, and dig a little bit deeper into regular languages, show some other interesting properties of regular languages, identify some interesting connections, and I'll even actually start the lecture with a very nice, cute application of DFAs, so you can see, like in real world situations, how DFAs can be quite useful. Okay, so that's it for me for today. Thanks everyone, and I'll see you guys tomorrow.